Perhaps you noticed that the behavior of my stack doesn't really depend on the fact that it's holding strings. And in Java, we have a nice way to specify that we might have different things in our stack without actually having to rewrite the code. This is called a generic type. And it's a somewhat complex subject, so we're just going to skim the surface of it. But the idea here is that we're going to have a parameter on our class, which is a type parameter. It's written in angled brackets in Java. And what we'd like to do is have a field here that instead of holding an array of strings, holds an array of things of that type. The actual execution of code with generic types is not complex. It's easy to understand. And let's look at the execution of the example code first. So what I'm going to do here is create two fixed capacity stacks. One here is going to hold integers with size 5, and one is going to hold strings with size 3. So what I can do here is create the first stack with capacity 5. Note that this stack is dedicated to hold integers, whereas the second stack is dedicated to hold strings. One thing worth noting in Java is that the generic type is not actually stored at runtime. This is all done in the compiler. The compiler will check to make sure you don't confuse two stacks, but it's not actually around at runtime. This causes some problems in the language. The reason is that this generic capability was added fairly late in the language, and therefore it's not the most beautiful thing. Nonetheless, it's useful and we will use it. So what we're going to do here on line 37 is push a number into stack 1. We can push another number, and it behaves as you expect. What I can do over here is push strings. So I can push ducks and geese, and everything works just as you expect. If you try and confuse the two stacks, you'll get in trouble. But before I show you that, let me back out to the ugly thing about stacks. So in my constructor, what I'd like to do here is to say, well, I'm creating an array of type T, and what I'd really like is to allocate a new array T with a given capacity, so the given type and the given capacity. Unfortunately, if you do this, you get a compiler error in Java, and the error reads, you cannot create a generic array. So why not? Well, they just decided we shouldn't do it. So that's an annoying fact. So what do we do instead? Well, we have to create an array of objects. But if you do this and leave it alone, you'll get another error, which is there's a type mismatch. Okay, you're creating an array of objects, but they really should be of type T. And that's annoying. So there's a feature in Java to get around this, which is called a cast. So I'll do a cast here. And yeah, it's compiling now, but now I'm getting a warning. And this is annoying too, because it's saying this is an unchecked cast. What does it mean by this? It's saying that this is a cast that Java cannot check at runtime. It cannot check that this array actually is an array of T's. And you can see that when you look at these purple boxes, because they don't tell you what type they're holding. This does not say anywhere that it's a capacity stack of strings. This doesn't say anywhere it's a stack of integers. And so at the runtime, it's not able to check this cast. So fine, we get a warning, but it's easy to get around this warning because we know this is not a problem. This is one case where we will suppress the warning. And so this is the pattern we're going to use for generic array creation. This is only a problem mixing generics and arrays. So given this rather ugly bit, it's not that bad. This is not something I will examine you on. I don't expect you to remember this particular incantation. You just shouldn't be shocked when you see it. It's fine. If you ever need to do it, just come here, copy and paste, okay? It's not something that's worth spending a lot of energy mentally on. It's just sort of an artifact of the way the language evolved over time. So what's good about this, though, is that once I have this capability, unlike Python lists where you can put integers and strings, You can mix them arbitrarily in Python. That's not true here. So when I say that S1 is a stack of integers, it means only integers. When I say S2 is a stack of strings, it's only strings. So if I try, for example, to push a integer onto the string stack, I'll get an error here, which says the method pushString cannot be applied to an integer. Right? So this is the big advantage, if you like, of generic types. So that's Java generics. The generic class has a type parameter, and the type is not stored at runtime. Another feature of Java we'll be using is interfaces. I'll walk through one such interface called the iterable interface. But in order to show it to you, I need to show you something called an iterator. The idea of an iterator is to go through the elements of a data structure without imposing on the data structure itself. This is a design pattern, and you'll learn more about design patterns in your software engineering courses, such as SE 350 or SE 450. But this pattern tells us that when we need to go through the elements of an object, we should not store the index we're using to go through those objects in the structure itself. Instead, this should be stored outside the structure in a separate object. This is what the iterator pattern does. Here we have an example, 2 stacks, one with 2 strings, one with 3 integers. And what I'm going to do is just go through the elements of the stack with 3 integers. To do this, I'm going to create on line 58 what's called an iterator. So let's see what happens when we do that. We're going to invoke a method here of the stack called iterator. So note that I'm invoking this on stack 1. And so here's the method. It doesn't do very much. All it does is create an object and return it. So I'm going to call the constructor of this reverse array iterator class. This class is interesting. It has only one field called I, but as we'll see when we create objects of this class, it has a special hidden field called this $0. This field, when the constructor starts to execute, needs to be initialized, and what it's going to be set is to the surrounding object. So in our constructor here, we will bind this $0 to whatever this was for the calling function. So in particular, what's going to happen here is this $0 is going to be bound to the stack that created this iterator. So the picture looks like this once we get to line 32. So we haven't actually done anything. We've just associated the this $0 with the stack that is creating this iterator. It's a little confusing because we have this and we have this $0. Note the difference. The constructor of the iterator is of course pointing to an iterator object with this. This $0 is not the iterator object. It's the stack who created this iterator. On line 32, we're going to read out in and place it in num occupied. Now you might wonder where I'm finding in. So in order to find in, I follow the this pointer, but note that there's no in stored here. That's the purpose of this $0. If I can't find a field following this, I follow this and then this $0 and I use the field from here. So the value I will use for in is 3, and what we're going to store here is 3. Then I'll initialize the field of this object, that's the reverse array iterator. Currently I is 0, now we'll set it to be num occupied minus 1, which is 2. At this point we can exit, and what we've done is created this reverse array iterator, and we'll return back to our main method. So back to our main method, and in our main method we will then go through the elements by invoking these two methods called hasNext and next. So to ask whether or not the iterator has an item, we say, well, does it have an item? Note that the iterator is currently saying it's pointing at element 2. 2 is at 31, so it's going to go through the elements in reverse, thus its name reverse array iterator. So we have an item. So when we go into the hasNext method, it will return whether or not I is greater than or equal to 0. So as long as I is greater than or equal to 0, this will return true. At that point, on line 60, we'll invoke that next method. This will go and get the next integer out of the array using the iterator. Note that I'm not popping the integer, I'm just looking at it. So it's different from pop. What I'm doing here is getting the result. I'm decrementing my cursor, I, but I'm not changing the number of things in the stack. So when I call the next method here, what does it do? Well, it's going to get a of I. And note again, a is not a local variable of the next method. A is not a field of the iterator. Instead, where is a? It's found by following the this $0 pointer to find the array. So we'll look at a of I, and that'll be the number 31. So we'll store 31 for our result. Then we decrement I, so we'll say we've seen 1, and now we can return the result that we saw. All right? This process is repeated again for 21, and finally again for 11. But at this point, when we execute line 38, note that the index goes negative. So at this point, I is -1. So the next time we call hasNext, hasNext will return false because the index is not greater than or equal to 0. And thus the loop exits. So that's the iterator pattern. It's fairly complex, but it is very useful. And in Java, this is a very common pattern. So let me run this code without drawing anything. When I run the code, it just prints out what's on the stack. Note that I'm doing it twice. I did it once by invoking the iterator explicitly, but I've also done it here using a special syntax in Java, which is available for iterable objects. So because my stack is iterable, I can use this nice syntax, which is very familiar from Python. It's like saying for the integer in the stack, I can print them all out. This syntax is only available if you actually implement the iterable interface. So simply removing the words up here, if I say implements iterable I, if I remove that, I will get a compiler error here saying you can only iterate over an array or an instance of java.lang.iterable. So because I removed the indication that the stack is iterable, this syntax is no longer valid. So if I put this in, then it compiles just fine. And I can use this sort of friendlier syntax for going through objects. Programmers like nice syntax, but somebody's got to do the work of implementing the grunge under the hood for them. So I know in your intro class, you could use nice syntax like this. In this class, you're learning how to implement that grunge under the hood that's required for the pretty syntax to work out. Iterators are fairly complex, and I won't ask you to code them on exams or things like that. But I want you to be able to read the interface here and understand what it's doing.